large sample confidence intervals. Recall hypothesis example 7. In a sample of n equal 40 tosses of coin, the proportion of heads, p hat, 30 out of 40, or 0.75. If the coin is evenly weighted or fair, the proportion of heads in the long run should be 0.5. There's a 50% chance of heads, 50% chance of tails, so if it's evenly weighted, heads and tails should turn up equally often. We tested the following hypothesis at the alpha equal 0.05 level of significance. H naught, P equal 0.5, the coin is evenly weighted, versus HA, P not equal to 0.5, the coin is not evenly weighted. We computed a p-value of 0.0016, which is less than our desired level of doubt, alpha equal 0.05. Thus we rejected H naught with 95% confidence and concluded that the coin is unevenly weighted. Now we're going to adapt empirical rule part 1.96. We call it empirical rule part 2, but more precisely it's part 1.96 that tells us that if p hat has a bell-shaped graph, then 95% of the z-scores for p hat are within 1.96 standard deviations of p hat. So as an exercise, we're going to use this to do what's called a confidence interval for p. So the formula is p hat plus or minus 1.96 times square root of p hat times 1 minus p hat all over n, and we want to create a 95% confidence interval for the population proportion. And it'll become clear, I think, once we compute the interval, how to interpret it. Anyway, here's the formula, so we want to plug in the numbers. So p hat is 0.75, that's our sample proportion, plus or minus square root 0.75. 1 minus 0.75 is going to be 0.25, and our sample size was 40. So that was all from the original information. We had n equal 40 tosses of the coin, the proportion of the heads, p hat 30 out of 40, or 0.75. Okay, so I'm going to do I forgot the 1.96. So this is times 1.96. Okay, so I'll do what's under the square root first. 0.75 plus or minus 1.96. And then if we do what's underneath the square root, we can do push the second key, and then the square root is over the x squared key, and the square root symbol comes up. 0.75 times 0.25 divided by 40. I get 0.06846,532. Okay, 0.06846,532. Okay, so this I computed this part separately because this is actually an estimate for the standard deviation of p hat, and sometimes it's reported separately. And then we want to multiply this by 1.96, so equals 0.75 plus or minus, and then 1.96 times that number there, times 1.96, 0.13419227. So let's see if I have a pen here. I don't think I do. Okay, so this is here we are. Okay, so this is the an estimate for the standard error of p hat, and this is what's called the margin of error here. And sometimes those are reported separately. Okay, so so then if we want to add and subtract this expression here, I'll do the subtraction first. So it's 0.75 minus the margin of error. We can store this in the calculator. We do stow and then equals. That we don't have to retype it. And 0.75 minus second recall equals about 0.615, 0.615807973. And if we add the margin of error, 0.75 plus the margin of error, 0.75 plus second recall equals about 0.884, 0.884192027. So if we round this off, this is approximately 0.616 to 0.884. So that tells us that we're 95% confident that the proportion of heads in the long run is going to be somewhere between 0.61 and 0.884. So that so we can use that to test the hypotheses. We tested the hypotheses more directly previously. We computed a p-value, but we can also use the confidence interval to test the hypotheses because the null value of 0.5 is not between 0.6 and 0.8. That means we reject H0 with 95% confidence. Okay, so here's the computation again. Conclusion: we are 95% confident that the proportion of heads in the long run would be between 0.616 and 0.884. And a few comments. Confidence intervals can be used to test hypotheses. In this case, because our null value of 0.5 is not between 0.616 and 0.884. See if I get a better copy of this here. Because the null value is not between 0.616 and 0.884, we reject H0 with 95% confidence and conclude the coin is unevenly weighted. Another comment: the quantity 0.068 is an estimate for the standard error, also called the standard deviation of p hat, and is sometimes reported separately. That was the this expression here. Is the standard error of an estimate for the standard error of p hat, and the quantity 0.3134 is called the margin of error, and that's also sometimes reported separately. This is the margin of error. That tells us how much we might be off by. This is our point estimate is the 0.75. Margin of error tells us how much we might be off by. Often it's expressed as a percent. So it's approximately 0.134, or if you multiply by 100, that would be 13.4%. It's called the margin of error, sometimes reported separately, especially for public opinion polls. Like if you may have seen it in the newspapers, like when they report, for example, let's say 38% of the voters support Biden for president. They'll usually give oftentimes they'll give a margin of error of 2% or 3%. Our margin of error is relatively high here because we have a sample size that's a little bit on the small side. When they do polls for to predict election outcomes, usually they're polling a couple thousand voters, and then you have a smaller margin of error. So they'll usually report a margin of error of 2% or 3% when they report make predictions about who people are going to vote for. So anyway, that's it for this presentation. So